for the introduction. It's a great pleasure sharing with you some of my expertise in astrobiology. I've seen a previous lecture on the European Institute of Astrobiology Academy, and it was really impressive. I hope I will not let you down about this. So we are actually looking for life, but when we are looking for life, as NASA has coined it, we are looking for water, because we are looking for life as we know it on Earth, and on Earth, all life has evolved in water. So actually, the subject of my talk is the habitable zone, and the best definition of the habitable zone, there are many, many definitions, but the best definition is the area around the star where you can find liquid water on a surface of a planet with an adequate atmosphere. And this is very important because, as we'll see, not every planet, even if it's potentially habitable, its atmosphere sometimes does not let it be habitable. And we see it right away in the introductory slide. What we see here is the solar system, habitable zone in green, approximately between the orbits of Venus and Mars. These are the planets of our solar system. And here we see another star, not the sun, and it has also to date 5 planets that we know, and not all of them are in the habitable zone like in the sun. Here we have 2 planets which have been discovered by the Kepler mission, Kepler 62, and the 2 planets 62F and E are within the habitable zone. So let us see what is this habitable zone for the solar system. So this is a special slide. It shows not the whole habitable zone of our sun, but the more conservative one. Of course, if we have water on the surface of a planet, this depends on the atmosphere, but here we have the smaller habitable zone, and we'll talk later about what does it mean. Earth, for sure, is in the habitable zone of our solar system. Is Mars and Venus? Let's see. Mars actually used to be quite similar to Earth, and it had, in the past, liquid water on its surface, even in great quantities. This has been established already by the Mariner mission, several missions who captured pictures of the surface of Mars and show really gullies and flow channels of rivers. And later, this was in the early 70s, and later in the 2005, we had an mission to Mars, which continued until recently, actually, very long one. And this mission had found the traces of water geology. This was a geological mission, Spirit and Opportunity, 2 rovers, and they found proofs that rocks that only form in water, at least on Earth, are present on Mars. So in the past, Mars had plenty of water. Why didn't it remain? Because we know nowadays Mars is actually best described as a frozen desert. It's very dry and very low temperature. So what happened? What is the difference between Earth and Mars? Earth did conserve its liquid water, Mars didn't. So there are several causes. Let's talk about the main one. The blame is that Mars is much smaller than Earth. So it is not capable of holding such a thick atmosphere as Earth. And hence the atmosphere of Mars is less than 1% than the atmosphere of Earth. This makes a big difference in the evolution of water and the conditions that are enabling life. Because on Earth, we have the atmosphere that protects the water, protects the ocean, and it when it's sunlight, ultraviolet sunlight hits only in the upper atmosphere, it disintegrates the water molecules to hydrogen and oxygen. Hydrogen escapes to space. Oxygen is a chemical, very active, and it combines with the ground. But this happened in Earth only in the upper atmosphere. In the lower atmosphere, it is protected against this ultraviolet radiation. In Mars, this is not the case. So the whole water that was on the surface evaporated, actually was disintegrated into hydrogen and oxygen. And the little water that did not, it remained, froze, because Mars is also further away from the sun, and therefore the temperature is lower. And because of its very thin atmosphere, it also has very small heating of the atmosphere, what we call the greenhouse effect. So the water on Mars froze on the surface, in the poles, in the permafrost, in the ground, etc. Of course, on Earth, we also have oxygen because of the photosynthesis, but this is a recent phenomenon, just the last 2 billion years. So let's go to other, to the whole phenomenon in the solar system. And you are probably familiar with the Goldilocks story of Goldilocks, who visited the house of the 3 bears and tasted the porridge. One was too hot, one was too cold, and one was just right. So we can, by analogy, have the same story for the solar system and also for other stars. So in the solar system, Venus is too near to the sun and is a massive greenhouse furnace, which brings its surface temperature to 450 Celsius. Mars is too far and its atmosphere too tenuous, so it becomes a frozen desert. And only Earth is just right, distance and atmosphere. So the average temperature is 15 Celsius, which is good for us. Now let's look at the other hundreds of billions of planets in the galaxy, in our Milky Way galaxy. And I want to start with a headline, which was very important a couple of years, so even 2.5 years ago. The September 2019, they announced that they have found a water vapor in the atmosphere of an exoplanet. And this was a huge achievement, because this was an achievement done by the Hubble Space Telescope. But actually, people did not believe this achievement can be done even with Hubble, and they thought they need to wait for James Webb telescope, which was launched in last December. And the method, we'll get back to the method, how they found the water in the atmosphere of K2 18b. K2 is for Kepler, second Kepler mission. 18 is the number, and B means the planet, the first closest planet to its star. And why is this so important? Because this is a method that will let us eventually discover life or biosignatures, signs of life on other planets. Why is this so difficult? Actually, only about 2 decades, we know, 25 years or so, we know that there are for sure other planets around. Other stars have planets like the sun. Why is it so difficult to discover exoplanets? And of course, to discover signs of life. So if we take by analogy, if we try to find an Earth around Alpha Centauri, our nearest stellar neighbor, it is about 4 light years away. And if we suppose that there is a planet at 1 astronomical unit from Alpha Centauri, like the distance of Earth from the sun, the mission of detecting it would be equally difficult, like observing a fly 10 meters away from a lighthouse from a distance of 1,000 kilometers. Why is this so difficult? Well, there are 2 things. First, the angle is very, very small indeed. And second, the fly is reflecting, it does not have light of its own. It is reflecting, but a very tiny amount of the light of the lighthouse. So the mission to observe a very dim object, very close to a very bright object, is very difficult. And this is why we cannot actually, in most cases, directly observe the exoplanets, and we need to do it with the alternative scenario, alternative missions, alternative methods. The one method which is very well known, and this was the method that the first exoplanets were discovered, for which the Nobel Prize was won in 2018, if I'm correct. This is the radial motion. And this is based on the Doppler shift. Doppler shift is when we observe an object that is approaching us, the wavelengths are a little shortened. So for example, if we have emission lines or absorption lines, they are shifted a little to the blue side of the spectrum, and vice versa. If we have, as we say, we cannot observe the planet. So here is the unseen planet, but we can observe, and we know how this planet affects its star, its host star. And while the planet is orbiting the host star is not sitting fixed in the point, because there is the gravity of the planet causes it to wobble. A very small circle, because the planet is much, much less massive than the star, of course, but still, and this little tiny change in velocity, and it is also periodical. From this we can discover and deduce the distance of the planet from the star and the mass of the planet. So it's very, very interesting we can see, without seeing the planet, we can learn a lot on it. And the other method is a transit method. This was a method that Kepler's Space Telescope used, and it is based on the little eclipses or partial eclipses that the planet causes when it is so located, the orbit is within the parallel to the line of sight to the star. So it hides the star for it hides a small portion of the star for when it passes. Of course, if it's not the case, like here, we will not see any transit. So we can see here, I'll start the movie, we can see the planet will come from the left to the right, and while it is passing onto the star, we'll see a little dimming, little decrease in the brightness, which will be here. So here we have, here the planet is hiding the star, part of the star, and there was a little dimming. This dimming could be typically something like 1%, so a very tiny change in the light, and if it's a small planet like Earth, it may be 0.01%. Let's look at it again. So the planet arrives, hides a little, and this dimming is periodical. So we can also, from the period, we can calculate the distance of the planet from its host star. And knowing the luminosity of the host star, we can calculate the temperature or the surface temperature of this exoplanet. Of course, subject to its atmosphere, which we usually don't know. Here we have the data, how this is discovered. Every point here is an observation, and all the observations have been put on one diagram, a phase diagram, so like similarly to what we saw before. And we saw this is a usual brightness of the host star. Here there is a dimming of about 1.5% when the planet obscures a small portion of the star. And here we come to our, what we already mentioned several times, the Kepler Space Telescope. Kepler focused on small habitable planets that of the size of Earth, and it discovered within 5 years of its mission, it discovered almost 5,000 of those planets. And this is the method that Kepler used. It looked at only a small part of the sky, a part of our galaxy. So here we are, the sun, and it looked not even 3,000 light years, and more like 1,000 light years, but it looked on about, considered about 150,000 stars, and only a small fraction of those, about 4,000, it found dimming. And this is because, of course, not every star and planet have this alignment of the planet with a line of sight to the star. So it's not happening for most of the stars. We will not have the transit. Only for those who are lucky, that we are lucky to see them in the right location, in the right direction, we can see the dimming. And here are the first, after 2 years of operation, a view of the planets that Kepler discovered from the largest to the smallest. And we see the sum of the planets are larger than even Jupiter. Here, the radius is in units of Earth's radius. So this one is 19 times Earth's radius, while Jupiter is only 11 times Earth's radius. And there are many the size of Neptune, which is about 4 times the radius of Earth. And at that time, there were not too many that were similar size to the Earth, but this changed till the end of the mission, as we can see. Here we can see a quite recent diagram of the distribution, a histogram of the number of planets discovered as a function of the size. And this is actually not exactly the number, this is the average number of planets per star. So we have about 0.3 planets per star, very small, like Earth, and a bit larger. And then this was we call Earth size. And then we have about a similar number or similar fraction of what we call super Earth, between 1.4 and 2 times the size of Earth. And then again, about 0.3 per star, what we call sub-Neptunian, the size of between 2 and 2.8, while Neptune is close to 4. And much less the size of Neptune, and again, much less larger stars, like the size of Jupiter and Saturn. So here are, this is a solar system, and we see that these 2 columns are actually sizes not seen in our solar system. Okay, let's move on. What is also important about the star, and especially for our talk about habitability, is not only the size, but also the planet temperature. And here we see the first discoveries of Kepler. These were stars, planets which were giant planets, like Jupiter and even more, but also very hot. They were very close to their hosts, and therefore temperatures of molten lava and liquid iron, see? And later they found also little less hot planets, still quite hot. See here about 500K, and only later they found also habitable planets, which are, according to their distance from the host star, possible to maintain a reasonable temperature for life. That is, Earth is about 300 degrees Kelvin. And here we have again the picture we saw in the beginning already, the Kepler 62 system with its 2 habitable planets and more inner planets which are non-habitable because they are too close to their star. Note that the habitable zone of Kepler 62 is smaller than the habitable zone of the Sun because this star is dimmer. And to maintain a similar flux per unit area, which determines the temperature, we need the habitable zone to be closer as compared to the solar system. And here is the size of several hypothetical stars. This is sun-like stars. Its habitable zone is in green, and hotter star and brighter stars than our sun will have a larger habitable zone. Cooler stars will have a smaller habitable zone. And this is a famous system, the Trappist-1 system. And we see, if we compare its habitable zone to the solar system, here we have all the diagram of Trappist-1. It is within the orbit of Mercury, so much smaller than the solar system. So here we have the solar system, habitable zone in green again. This is Mercury, Venus, Earth. And if we look inside here, this tiny region, around this star, which is a star of a very special kind, it's called a red dwarf. It's a red sun, very dim, and therefore its habitable zone is much smaller. And within this small habitable zone, they found not less than 6 planets. And there is another 7th planet, which is outside the habitable zones. So this is probably too cold, but these 6 planets could, maybe this is too hot, but depending on their atmosphere, of course. So at least these 3 planets, D, E, and F, Trappist-1, D, E, and F, could have the right temperature for liquid water. And how, let's see now how we present the habitable zone in a diagram. Now, this is the stellar distance in astronomical units. And this is the type of the host star. Here, this is a red dwarf, very cool. This is can be represented by its temperature. So red dwarf typically is 3000 degrees Kelvin. And this is a star like our sun here, almost 6000. And the habitable zone is a region which depends on the stellar host. For smaller hosts, it will be closer to the star. This is Earth, the distance 1 astronomical units. This is for our sun. And the habitable zone of our solar system is roughly between these 2 limits. Brighter stars, hotter stars, have a larger habitable zone further away. Cooler stars, smaller, further in. But we can also represent the habitable zone in a different manner. Here we have again the distance in astronomical units, but this time in a logarithmic scale. And the host star is represented by its mass. It is also a synonym to its temperature, because if we have stars in the main sequence, its mass determines also the temperature. And what we had before, the whole diagram that we had before fits within this square. And because of this logarithmic scale, the habitable zone looks a little different, but again, it's a stripe for depending its size and size and the distance from the host star depend on the temperature or on the mass here, or on the luminosity of the host star. All these 3 quantities are related as long as we talk about the main sequence. And here we see our solar system. The mass is 1 solar mass, this M with a little dotted circle. And the type of star is G type, like our sun. Here is Mercury, Venus, Earth, Mars, Jupiter, Saturn, etc. And we see this is a habitable zone. Now let us see another representation of the habitable zone. This time we have entered another information, which is 2 kinds of habitable zone. The habitable zone between these 2 blue lines, and a little larger habitable zone between the red and orange line. We'll talk about it in the next diagram. So again, this is a similar picture. Here we have our sun, the solar system. Venus is on the inner verge of the habitable zone. Mars is close to the outer. And again, here is the distance from the star. But we can represent the habitable zone not with a distance from its star, but the amount of radiation it receives from its star. And this is the flux received per unit area from the host star. again, three kinds of host stars, the temperature of the host star as before, but this time this is a little different. So this is the energy received by the planets. One is Earth. Here is Earth for our sun. And the green area here is the habitable zone in this representation. And here we see some of the exoplanets discovered. Never mind. Note that the area, the distance, what is represents the distance is increasing in this direction. So the flux per unit area is decreasing in this direction. So this is Earth. This is 0.1 of the flux that Earth is receiving, and this is too little. This will be too cold. So this is too cold. This is too hot, and the green area is the habitable zone. And this is a similar representation. Again, a temperature of the host star, and we have two kinds of habitable zone, or two definitions. This is Earth flux per unit area, 0.5 of the flux Earth receives. This is 2 times flux. And there are two kinds of habitable zone. One is a conservative habitable zone that makes an assumption about the climate. The reasons that we have two kinds, or actually a whole variety of habitable zones definitions, depends on that we don't know precisely how the climate model depends. So this is for a conservative climate model. And if we have a more optimistic climate model, the habitable zone will be this whole, a larger area. Again, in the unit of flux per unit area. And here we can see how this depends, how our sun is evolving. So you perhaps know that our sun has in the past shining less bright than now, about 30% less. And the sun is evolving. Every star is evolving. And in the end, our sun will turn into a red giant and will be much brighter, and the habitable zone will be much further away. But here we just look at 10 billion years of the sun till it becomes a red giant. And we are now at the point of 4.5 billion years. There has been a small, as we said before, the brighter the host star, the further away the habitable zone. So the habitable zone is evolving along with the luminosity of the sun. Now here we have the conservative habitable zone, is a dark green, and the light green is the more optimistic habitable zone. What we can see here is also that at a certain point, for Earth at least, the habitable zone will leave the orbit of Earth. So while in this time until present, we are still in the habitable zone, depending on the model, in about 1.5 or in about 1 billion years for the conservative model, and in about 3 billion years for the optimistic model, Earth will become non-habitable. The oceans will boil and evaporate, and it will become more similar to Venus. And here we have again a representation of this habitable zone. Again, here is the effective flux, and here we can see the limits. In the optimistic model of the habitable zone, the borders are determined by Venus, assuming that until recently Venus had water. So this would be border. Now it's already out of the habitable zone, but this is how recently Venus, this is of course for our sun, but for a smaller planet it will be here, for smaller stars and a less bright star it will be here, for brighter stars it will be here. So this is the inner border of the habitable zone, and the outer border can be determined by ancient Mars. Ancient Mars, it means that we have Mars, as we saw at the beginning, had water in the past, in the far past. And this line, the brown or orange line here, is the line that shows the ancient Mars. So now we have two kinds of habitable zones, the conservative one and the optimistic one. Here, a last representation of the habitable zone. Again, the temperature of the host star. This is the flux. And what we can see here is the habitable zone. Dark green is the conservative one, light green, early Mars till recent Venus is the optimistic one. Here is the solar system, Venus, Earth, Mars. And here we see a lot of discovered planets by Kepler. And what we can note here is that most of the planets were large planets, similar to Jovian size, these yellow things. Only a few were super-terran or terran. But almost all of those were discovered, all the habitable planets around with a size of similar to Earth or super-Earth were discovered around red dwarf. And this is a technical feature that it is easier to discover small planets around red dwarf because our technical limitation of this method. Now let us talk about signs of life in exoplanets, in exoplanet atmospheres. Of course, the most direct sign of life which we could possibly find within a few years would be oxygen in its atmosphere. Oxygen would be a sign of photosynthesis, but the oxygen alone may be not enough because it may also be formed by non-biological processes. So we need other things like liquid water, water vapor. In one exoplanet, it was already discovered in 2019. We can actually make a spectroscopy of the host light transmitted through the planet's atmosphere, if it's transiting, and find different compositional signs. One thing that could be associated with life would be methane, which is a sign of biotic activity, although it can also be discovered, produced non-biologically. And to end, let us show the method that was used to discover the water vapor in K2-18b. And also the same method will be used to discover biosignatures in the atmospheres of many exoplanets using James Webb Space Telescope, and in a few years also ELT. So let us see how this is done. The point here is that different gases have different absorption cross sections, and in different wavelengths, they may be transparent or not transparent. So here we see again this transit diagram. when the planet is hitting or begins to obscure the host star, it goes down and stays roughly constant till the planet leaves the circle of the star. And this is for the continuum in green. However, if we look for another wavelength, another band, where the atmosphere is opaque, so we assume the atmosphere in the continuum is transparent. So here's a dark circle is a rocky planet, and the bluish ring is the atmosphere. Now, if we look on wavelengths in the water band, where the water it is in the infrared, and there it is opaque. So if the atmosphere has enough water vapor, not only the rocky center will be opaque, but the planet will look bigger, because also the atmosphere will absorb the light, and it will be a larger decrease. So it will go lower. So if this goes down maybe 0.01%, so this can go down maybe 0.02% for an Earth-sized planet. And still similar for methane, for example. If we look at the methane band and we see a difference between the continuum and the methane band, we'll see that the atmosphere contains methane, and so on. So this is a method that we'll actually we hope to discover in the near future, in the next year's biosignatures. And to end up, the density and composition can also be determined by this method. We actually need to measure the mass by the radial motion method, and the radius by the transit method, and we can see the composition of the planets. So if we have this diagram shows the mass x-axis and the radius on the y-axis, and we see a few planets that we know from the solar system, like Earth here and Venus here, Neptune and Uranus. And we can calculate what will be the average density, and therefore the mass and radius of a planetary formation. You see that it is not precisely the m/r cubed, because this is neglecting the pressure. And if we have a planet, it of course is the gravity pressurizes it, and we'll have this curve. So planets that are falling here are watery, planets here are rocky, and planets here are mostly iron. So we can see these are some planets that have been discovered, and some of them are really gassy, like Neptune and Uranus, and others are rocky. So we can discover or determine the composition. And this brings us to the end of liquid water and the habitable zone. Thank you for listening.